for the afternoon poster session. Okay.
Okay. So one of the duties of the organizer is to fill the gap. And since Atama couldn't come for family reasons, so I'll give sort of a 45 minutes talk on elasticity and unelasticity, particularly from experimentalist point of view. I don't have a beautiful picture of scenery. I could have brought something from Tennessee. Instead, at least it's more beautiful to me, is this picture. This is a picture of spallation neutron source, $1.4 billion facility that took 6 or 7 years to build, and still we are building. And I have been at the University of Pennsylvania for a long time, but I moved to Tennessee 6 years ago, mainly to be involved in this neutron facility. This one is by far the best facility in the world. The power of this facility is now 1 megawatt. It's just if you measure it in terms of power, which is 5 times larger than the competing facility. And still we are growing. We plan to go to 1.5 in about a year or so. And in 10 years, we are planned to go to 5 megawatt. So it is already the strongest neutron source in the world, and it will grow to even to higher level. And I'm running an institute called JINS, Joint Institute for Neutron Sciences. Here it's under construction. This is a little bit old picture, so that's the today. My office will be here. And this is the place for scientists to discuss. The other building is to run the facility. But here we get together, have tea and coffee, and plan on what to do. So before I get on, I'd like to say a few words about metallic glasses, how metallic glasses are different from some other classes of glasses discussed here, such as colloid or molecular glasses. For instance, it is more harmonic in terms of interaction, and the structure is simpler, so we can get down to atomic levels, and then discuss experimental observation of elasticity and unelasticity by X-ray diffraction. Many things that we have been discussing so far can be directly seen. And first, as you know, bulk metallic glasses, now you can really make bulk. That's centimeter here. However, that is very different from hard sphere system. It's sort of ironic that Bernal, who proposed this dense hard sphere model, was actually thinking about metallic liquids. But hard sphere system does not describe the system quite well. This is the change in the volume or density upon melting. Okay? In case of hard sphere model, the density of or packing fraction of FCC is 74%, as you know. But dense random packing is 64% or so. So if FCC metal melts, then volume changes about 17%. And that is true for rare gases, argon and neon and these guys, which are described by Lennox Jones potential. Some of you think the Lennox Jones system is a soft glass. No, it still is hard for me. Metallic glass is even softer than the Lennox Jones system. Lennox Jones system, like these, again, changes the volume by 15%. That's for the inert gases. But many of the metals, these are elements, not compounds, show much smaller changes in the volume upon melting. As you can see, maybe average is 3% or so, some of them even negative. And this comes from the fact that the metals or semi-metals and some of the covalent system as well, the free electrons really screen the charge fluctuation, and the potential is much more harmonic. Another indicator is the ratio of a melting temperature to boiling temperature. The melting temperature tells you about the sort of curvature of the potential at the bottom, right? It's related to phonon frequency, so it's an indicative of the curvature of the potential. TB boiling temperature is the depth. It's proportional to the depth of the potential. So the ratio of Tm to Tb shows how tight or how wide the potential is. So again, the rare gases has a ratio of almost 1, but other metals has a ratio of 0.4 or something like that. So all of these show that the metallic system has a softer potential. It's a really soft system, and maybe closer to the soft colloid rather than the molecular or hard colloid. And this shows you a little bit difficult to see, but that's the Lennox Jones potential. This green is Lennox Jones potential, and blue is a potential we use to describe ion systems. As you can see, that the Lennox Jones potential is much more asymmetric, right? And blue one is more harmonic. One parameter to show this harmonicity is so-called Gruneisen constant, that the ratio of the phonon frequency divided by volume, or change in the phonon frequency with respect to the change in volume. And for Lennox Jones potential, this Gruneisen constant is 2.5, while for this ion potential it's 0.88. And many metals show Gruneisen constant of about 1. So Lennox Jones potential is still hard for the metals. Now, so therefore, as I discussed yesterday, local volume fluctuation is evenly plus and minus. This is the distribution of atomic volume. That's a pressure. I'll discuss it next week. But you can see the distribution of a local atomic volume is wide and equally positive as well as negative. So atoms can be expanded as well as compressed. Atoms are easy to compress. And amplitude is almost nearly 10%. So there's a lot of density fluctuations, and that's again the basis for the model coupling theory. So model coupling theory, people know that the system is harmonic and fluctuating, and somehow there's a disconnect between this kind of density fluctuation thinking in model coupling and hard sphere thinking, and such as jamming. I'll mention about jamming next week. Anyway, and then also that the structures are simpler than, say, polymers, so we can discuss atomic details, and we'll show an example of that. Atomic bonds are fairly well defined in terms of nearest neighbor. Nearest neighbor and second nearest neighbors are fairly well separated, so we can define the bond. Now, elasticity and unelasticity, you already heard a lot about this. Elasticity is a sort of instantaneous response to the stress, and unelasticity is a delayed response to the stress. However, the point is, in glasses, actually this relaxation time, tau, has a very, very wide distribution, from a minute to even a time scale of phonons or picosecond, okay? So actually, this is a little bit misleading, because this definition of elasticity depends on the time scale, which Michael already mentioned. It's important to know the time scale. Actually, this the response of this ratio, or C, is the frequency-dependent quantity, okay? The response to a stress is in a frequency-dependent quantity, and at high frequency, the response becomes less. You know, at low frequency, you can pick up all the fast processes. Huh? As you increase frequency, that some of the slow process cannot follow, therefore the response becomes smaller. So this apparent elastic constant is frequency dependent. It depends on the time scale of your measurement. And therefore, that observed strain includes all these fast processes, process with the time constant shorter than the measurement time, okay? And so actually, that's what it is. Elastic plus some of the fast unelastic part is measured as a sort of, you know, elastic quote unquote. And we can see this. So I'm going to show you that by X-ray diffraction, we can separate these two. And you have a very significant contribution of unelastic part for the regular experiment in which you pull, you know, at the rate of second or something like that. That's the point. And again, even ultrasound measurement is not fast enough. An example of that is that that's the sound velocity measured by ultrasonic measurement. And that's the sound velocity or the slope of the dispersion measured by inelastic X-ray scattering, which is much faster, okay? And this, if you extrapolate to 0, there's a difference. That means there's a dispersion process between ultrasound and X-rays, X-ray measurement. And even that is slow because we are talking about, you know, process here of the order of terahertz. And their process is even faster than terahertz, which responds unelastically to the system. So, and on top of that, there was also discussion about affine deformation. Affine deformation means, Lindsay Greer, I think, mentioned this, you know, uniform deformation. In other words, that that's the vector that the designated position, say, position on one atom before deformation. This is after. And this is connected by a tensor because this is a vector, right? And then this tensor, if a tensor is uniform, okay, everywhere, then that's called affine deformation. In reality, this tensor is not uniform, and we'll get into that. So that's a non-elastic, non-affine deformation. And for glasses, because structure is not uniform, this affine behavior actually does not occur, and then the motion is non-affine, non-collinear. That was noted earlier by Dennis Ware. And right after that, we also did some simulation, and not right after, many years later, simulation, and found that it is not only non-affine, not only non-collinear, but unelastic. That's the point. So, okay, yes. Sorry? This? Yeah, stress-strain curve, yeah. No, that's just a stress versus strain.
No, but different X corresponds to aluminum composition.
No. Let's not get into that. Yes, but I'm not worrying about that yet. Right? Now, this is what Dennis Ware said. If the change is affine, you know, each atom displaces linearly the same way, and then this proportion is really you know, proportional to distance. But because the structure is not regular, disordered, so some of them go left and right, and the motion is going to be non-collinear. That's what they said. And that makes sense, right? The response should be non-collinear. But we found that actually more than that, some of the bonds are cut. That means nearest neighbor becomes second nearest neighbor, right? And some of the bonds are formed. Second nearest neighbor becomes nearest neighbor. So displacement locally can be 1 angstrom, even though the strain is very, very small. if you put in a very small, say, 0.1% or even less, somewhere big changes are happening. And that's what we noticed. But simply the number of this change is proportional to the stress or strain, macroscopic strain. Therefore, it looks elastic. You know, this is number of this such a bond rearrangement versus strain, and it's kind of linear, right? So it appears elastic, but actually it is not. It is unelastic. And we decompose the total strain into elastic, truly elastic portion and unelastic portion. So in the beginning, elastic portion is larger, but soon, you know, unelastic portion wins. And that's the message from the simulation. So we wanted to prove this by experiment. Now,
so, Takeshi?
Yes.
Here. Can I ask a question?
Yeah.
So when you talk about anelastic, you're mostly talking about the fact that it's not affine, but
No, not only.
do you always mean that it's reversible in this case as well?
Irreversible.
Irreversible, but
Locally irreversible.
but but you're distinguishing it from plasticity. So is it reversible by like if you were to strain in the opposite direction, it could be recovered? I mean, that's another.
Right. Exactly. That's an important point. Important point is the time scale. So if you do a slow experiment at an experiment, a lab scale, then all these processes are fast. So it looks reversible. And also looks reversible in ensemble average. Not all the atoms go back to the same place. Actually, it says, you know, this goes and then next guy comes back or something like that. So microscopically irreversible, but macroscopically reversible. And also there have been some discussion, Lindsay Greer discussed this paper of measuring strain by X-ray diffraction. You know, in crystals, simply by tracking the Bragg peak, you can measure strain and stress and strains. So they did the same thing, and here, and the parallel direction and perpendicular direction, you know, move this differently. The peaks move differently. So from that, you can define strain. Now, this is again the same way that if you change strain, the peak position move and all that. Now, strange thing is that if you, Lindsay also showed this, if you consider Young's modulus, in other words, if you divide strain by the stress, or no, the other way, stress by strain, okay, then this apparent Young's modulus depends on the distance. You know, somewhere nearest neighbor is harder, and then it's softer and stuff like that. It sort of makes sense, but actually it's wrong. It's completely wrong. I'm going to show you why this is wrong. And the same happened with the analysis by Todd Hafnagel. Here, this strain is not constant, but it changes with the distance. Apparent strain changes with distance. Now, there are two problems with these analyses. First, I'll show you, but they used the Fourier transform, which actually is valid only for isotropic systems. For anisotropic system, you cannot use Fourier analysis. Second, that elasticity and unelasticity have been mixed up. They are not separated. So that's the crux of the matter or focus of my talk. Now, the equation that everybody uses is this equation. You have seen this many times, right, already. It's a sine Fourier transform. And then they use this equation, for instance, along the stress direction and in the 90 degrees transverse direction, right? Actually, you cannot do that because this equation comes from this Fourier transform in 3 dimension by vector q, and then by spherically averaging this, you get this equation. But you don't have the isotropic system. So this equation is invalid. The right thing to do, we have shown this quite some time ago in 87, is to expand this vector-based structure factor by spherical harmonics, and also pair density function also by spherical harmonics. All right? then these coefficients are related by this transformation, spherical Bessel transformation. And J0 is sine x over x. Okay? So J0 isotropic part is a simple Fourier transform. Right? But for higher order, we have to use spherical Bessel, not the Fourier transform. And difference is small but important. Okay? Todd Hafnagel says, it's the same thing, but it's not quite the same thing. So this can be now measured completely by using the system. Several people showed. In fact, Ken Kelton last week discussed this synchrotron measurement with 2D detector. This is the two-dimensional detector. Sample is here. Synchrotron synchrotron beam come not white. High energy synchrotron beam come here, and this is a sample and detected by this two-dimensional detector. This was first done by Simon Billinge, who is my former student, and this very effective way allows you to get the diffraction pattern even as fast as 3 milliseconds. Okay, you can get some pair density function in 3 milliseconds. We usually spend more time because we want to get high quality, high statistics data. We usually count like 100 million counts. But you can get 100 million counts in 10 minutes or so. It's fantastic. And that's the sample in the heater, reflective heater. So what you get is this kind of pattern. I think you've seen this before, right? That's a two-dimensional detector, and the color shows intensity. So this is when the sample is isotropic. You get this circular symmetric pattern here. And from the intensity, you can get this structure function. We've seen this many times, right? And by Fourier transform, you get this pair density function here. Okay? And you can see how good statistically this is. Now, again, this is when the sample is isotropic. What happens if you deform sample, for instance, elastically deform or plastically deform? So it's a little bit difficult to see because this circle becomes ellipse. So what we did is to take a pattern with the axis, axis here, and then rotate by 90 degrees, okay, and to access that, and took a difference, right? This shows the difference between these two patterns. And so you can see that this, in this direction, that this peak red is positive and blue is negative, okay? So peak moved down along this direction, and here peak moved out, okay? So you can see the clear anisotropy of the pattern. So we apply, again, spherical harmonics analysis on this result, and that is the 0th order isotropic part, okay? Isotropic part with the applied stress. This is stress is applied at room temperature, so this is within elastic limit, right? So the strain looks linear by all means. And here we have all these plots, but you cannot see the difference, okay? Isotropic part almost, completely remains the same. There's small change because of Poisson ratio, but it's really, really small. So isotropic part does not change by the elastic stress. On the other hand, that the anisotropic part, this twofold part, changes like this if you increase the stress. And this is the blown up of this first and second peak region. As you can see, the pattern does not change, right? You might think that the peak would shift. No, it is not. The pattern is the same, but simply amplitude changes. Amplitude changes with the stress. So what you see in the S of Q along one direction versus the other is the sum of this twofold term and zerofold term. Okay? So, sorry? It's small. In this case, few percent, 2 or 3%. the twofold term is much smaller than the isotropic part. Huh? I can't hear you. Yes, in situ. Yes. This is measured under the stress. Yes. So, we now apply spherical Bessel transform, which takes this form for 0th and L equal 2 order term. L equal 4 is completely absent, and there's a small term with L equal 6, but it's much, much smaller. So in practice, L equal 2 is enough. And this is because stress is L equal 2 tensor. If you break up the stress component, stress tensor, it breaks up into L equal 0, which is a pressure term, and 5 L equal 2 terms. So again, that's the isotropic part of the pair density function. Again, it does not change much, with the stress. But anisotropic part, twofold term, changes with the stress. And as you can see that this extends quite a bit. It's not only here, but it extends quite a bit in distance. So that's the anisotropic part of the pair density function, right? And if you look at the first peak part again, the pattern does not change. Simply amplitude changes with the applied increased stress. Okay? Is everything clear? Right. Now, what does it mean? Yes, uniaxial component, like y20. Z squared minus half of x squared plus minus squared. So what does it mean? First, we can show, it's in our older paper, but if the strain is affine, okay? If the strain is completely uniform and affine, then this L equal 2 component is directly proportional to the derivative of the isotropic part, right? That comes right away from the from geometry, right? So the derivative of the isotropic part times R times strain is equal to this twofold term. So you can tell right away by comparing twofold term and zerofold term whether that is affine or not, okay? So if you do that, that's the observed twofold term, and the black one is this derivative times R, and with the appropriate amplitude of strain. And they're not, they are pretty close, right? It's not bad. That means this long-range part, okay? Long-range part is purely affine. But there are some differences at short distances. That means that's a non-affine part. So non-affine part or unelasticity is quite short range. And if you go to the distance like 10 angstrom, all these are averaged out already, and it sort of apparently looks affine, okay? That's a very important statement. So the mechanism of anelasticity, in other words, the rearrangement, is very short range. It is not extensive as in, say, dislocation, okay? It's local phenomena. And this affine part or strain part, and indeed is linear with a stress. But elastic constant is wrong, okay? Elastic constant of this affine part is very different from the macroscopic elastic constant. So the affine part, which is the uniform elastic deformation, is a small portion, not small, but I mean, certain portion of the response. I'll show you. Huh? I'll show you. I'll show you. Experimentally, it's about 70%, and by simulation, which is much faster in time scale, it's about 50%. So anyway, the only part of the response is elastic, and the rest is inelastic, right? Even when you even the whole thing look elastic, and that's again the blow up of this part. Now, we can also do inelastic experiment, which is often called creepy name. That is that if you apply a stress and increase the temperature, and then wait for a while for inelastic events to happen, right? This temperature is below the glass transition temperature, but above the room temperature. If you go above glass temperature, of course, everything becomes equilibrated. So we stay below the glass transition temperature and apply stress, all right? Then cool down with the stress on. That is necessary because you want to freeze this change, okay? You don't want this event to recover. So you freeze the whole thing and then remove the stress. So the sample is in a kind of a, it has a memory of what happens at high temperature. So if you increase the temperature of this sample without stress, then it recovers to the initial state. But if you don't do that, at this time, when you remove the stress, the sample has some memory, so the structure is already anisotropic. It's not isotropic, it's anisotropic. And we can determine, we can observe this anisotropy by diffraction. Okay? And that's the change. So again, red one is the twofold term, anisotropic term of the sample which was subjected to this creep experiment. Right? It's no longer isotropic. And the black one is, again, derivative. So again, long-range part looks elastic, rather. We did this experiment way back in '87 too, but now we do it with this with much higher statistical accuracy. So again, clearly there's a difference between these two. That is due to inelastic events. Right? Okay. So let's compare this difference. We're not just looking at twofold term. We are looking at the result minus elastic part. Okay. You take you determine twofold part, and then subtract this the part which is proportional to the derivative or affine part. Okay. So we're just looking at non-affine deformation, and black one is due to elastic deformation, and red one is due to the creep. And remarkably, they look similar, right? There are some differences here, but that is due to the fact that during the creep measurement, we are subjecting the sample to high temperature treatment. So there's some change in the chemical short range order. So zirconium, labor. This is zirconium-based sample, the same composition, but in the creep experiment, there's some compositional change happens, while in elastic case, there's no change in compositional order. So that explains the difference between these two peaks. But basically, they look similar, right? So that is the inelastic part of this event. Again, there's not much going on beyond, say, 7 or something like that. So the change is basically very short range, and most of the change is happening at the nearest neighbor level. Is it clear? Right? This is an inelastic part, okay? Now, Solo Iwashita, who is here somewhere, did this simulation, a computer simulation, and extracted this inelastic part of this deformation, and looks just like that. And the important thing is that that's the first part, the first peak part. And you can see that if you integrate from here to here, you get positive value, right? Positive value. That's the same. It's a little bit more difficult to see it here in experiment, but if you do the same thing, up the first peak is up to here. If you integrate this, you get positive value. And that is the bond orientation anisotropy. Because of this deformation, bond in one direction becomes more numerous than the other. And early on, Michael also showed this picture, that we came to this picture, which we see also by molecular dynamics. We see this all the time, that if you have a configuration like this, it's almost dead. A configuration like this, and if I apply stresses and weight, then this bond gets cut. And instead, new bond is formed between this. So that's the effect of stress and bond orientational anisotropy due to this creep effect. Now, when we did this experiment, when Suzuki was my student, and we did this experiment in anticipation of a polymer result. If you pull polymer, then you line up chains, right? So we thought maybe you see more bonds in the direction of this stress. So Suzuki did the experiment and came back and scratching his head, and actually the result is opposite. Okay, so we said, wow, that's interesting, and then started to think about what's going on, and came to realize that in case of metallic glasses, because you can cut bond easily, so you get bond rearrangement. In case of polymer, you cannot cut bond, so you just line up that way, right? But in metallic glasses, this bond is easily cut, and then new bonds are formed. So actually, you form bond in perpendicular direction. If you stretch this way, you have more bond in perpendicular direction. And that's what this simulation shows. The total is positive. Actually, positive means more in the perpendicular direction in this particular instance. So that is the event what we see. Again, it's localized, and that is the breakdown of the strain into elastic part. Green is the elastic part, okay? And red is unelastic part. And blue is the sum of these two. So as you can see that the elastic or affine part is only 50% of the total strain. And the 50%, the rest, is unelastic. And as I said, this ratio is because this computer experiment is, you're pulling at a very high rate, and sample is small, so anyway, it ends up with this rather large unelastic part. And my estimate is, in the experiment, is about 70% elastic and 30% unelastic. But either case, it's a significant portion of this apparently elastic strain is due to this unelastic event. So in summary, that the structure of glass can be strongly anisotropic, and we can determine this by direct analysis. In this case, again, don't use Fourier transform. We have to use this spherical Bessel transformation, and then we can determine this anisotropy, and also by using the fact that an affine deformation is proportional to the derivative of zeroth order, we can separate affine portion and non-affine portion, or affine portion which is elastic and non-affine portion which is unelastic. And both in the creep and elastic strain case, we have very significant unelastic proportion of the changes. So, and they can be explained in terms of this bond orientational anisotropy, BOA. So this is a case where metallic glass is simple enough. It's an atomic glass. It's not like a polymer glass, which is very, very complex, or molecular glass. It's a very simple atomic glass. So we can come down to atomic process to analyze what is going on. And indeed, that relates to the Michael's STZ that he just discussed about this switching event. So we can even see here more or less directly that what this switching mechanism is. Again, very, very localized, and is due to this bond exchange. It's like Wall Street. So thank you.
So